Actually, I'm going to share the other screen first. All right. If you haven't already voted on when to have next week's review session, then please do so by Friday morning. I'm going to pick the time for that Friday morning. Any questions on anything? Where's the chat? Why am I not seeing the chat? There's the chat box. Okay, it's 10, so let's get started. I want to start actually by talking about something from a previous assignment. When people were convolving two Gaussians, people wound up getting basically e to the minus x squared over w1 squared plus w2 squared over something more times something like this. And I'm leaving out some details, but that was the basic structure of what people got. And then you were asked, well, what's the width of this convolved Gaussian? And a lot of people said this. But the width is the thing that you are dividing x by. So we could rewrite this as e to the minus x over the square root of w1 squared plus w2 squared, whole thing squared. And so this thing is the width. Now some people will say, well, which width is that? Is that the 1 over e width, or is that the full width at half max, or the 1 over e squared width? In this case, it happens to be the 1 over e width, but more importantly, whether you measure it as 1 over e squared, full width, half max, whatever, it's going to be proportional to that. And in most practical applications, what matters most, the thing that you spend the most time thinking about, is what is proportional to. At the end, if somebody says, well, I want to convert to full width at half max, then you multiply or divide by like logarithm of 2 or square root of logarithm of 2 or whatever. You know, some factor that doesn't really matter. But all of your thinking about how do we scale things up, how do we scale things down, depending on what you're trying to achieve, there you're entirely focused on this term. And if at the end you multiply or divide it by something that's somewhere between 0.7 and 2, who cares? Any questions on that?
So is that a rule of thumb, whatever your parameter is, your parameter, if it's divided by a square root of the form of a squared plus b squared, that would be your width of your function.
It doesn't have to be a square root. Whatever x is divided by, that's your width. I mean, in today's assignment, all right, you've got e to the minus gamma absolute value of x. And so if we want to know where this is 1 over e, then gamma absolute value of x equals 1. If we want this to be 1/2, then gamma absolute value of x equals ln of 2. All right. And so here, the width is 1 over gamma. All right. Because here you could rewrite this as e to the minus absolute value of x over 1 over gamma. So it's whatever x is divided by that's going to be proportional to your width. And this will be 1 over e if gamma absolute value of x is 1, 1/2 if gamma absolute value of x is ln 2. It would be 1 over e squared if gamma absolute value of x is 2, and so forth. Make sense?
Yep.
All right. Then let's ask a different question now about Fourier transforms. Let's ask the question, how frequently do you need to measure something if you want to detect a modulation at a given frequency? If something was oscillating once per second and you sampled 50 times a second, obviously you would measure that sine wave pretty accurately. So what I've got here is I've got a plot of a sine wave, and then we play with the frequency of the sine wave. We're sampling this sine wave once a second. I could have reversed it, and I could have fixed the frequency of the sine wave and varied the sampling, but I just said we're going to sample once a second. And if the frequency is low, I mean, here it goes through a full cycle in about a time of 13. So we get 13 points per cycle. With this, you could very clearly say, yep, that's an oscillation. It repeats every 13 seconds. Maybe say, no, we can't see it repeat every 13. But, if we were to play with X max, if I were to make that 50 and I were to, again, make that 13, you could say, yeah, all right, that repeats every 13 or so. That repeats every 13 seconds. So yeah, fine. We've managed to map that out. But then, as I make it even longer, yeah, here we can very, very clearly make out the details of that oscillation. But what if I make it high frequency? Before I do that and we look at the math in detail, there are plenty of high frequency oscillations that we don't directly observe in our experience. And so we don't even think that they're oscillating. We look at light, and to our eyes, light, say sunlight is steady, okay? Yeah, it changes throughout the day, but if you just look at it steady, you look at a light bulb that's on and nobody's playing around with the current or whatever, it's steady. But in fact, that light isn't steady. It's oscillating once every 10 to the minus 15, 10 to the minus 16 seconds. Okay, it's just that we don't sample it on that short of a time scale, so we can never possibly observe it. So as we make the frequencies higher, it starts to become very difficult to see what's really going on. For instance, here's a case that looks utterly confusing. It's actually a very high frequency oscillation. But if you were to try to collect this data, you'd look at it and say, well, that's junk. That makes absolutely no sense. This data, again, you'd say it looks like there's two oscillations going on here. And these oscillations have a period of, about 15 or 16 seconds, because that's where that peak is. Except actually you would say, sorry, down and up. You would say that they have a period of like 26 or so seconds. But of course, that's not what's going on at all. And as I turn it up even higher, at really high frequency, you would say that, oh, well, it's being sampled. Now here you would pick up an oscillation, and you would say that it's going down and up and down and up. So you would say that this is oscillating every 2 seconds. Because K is pi and K is 2 pi over the wavelength. So the wavelength is pi over, the wavelength is 2 pi over K. And anyway, what you should be seeing right now is that it is really hard to tell what's going on. Now, if I went up to higher frequencies, what just happened? Oops. 2 pi, 2 pi. If I go up to really high frequencies, again, it's just a jumble. And then if I go up to a really high frequency, I can actually get it so that we sample it at intervals of, well, here we detect something that's just completely wrong. Here we detect something that's just completely wrong. And the reason why we're detecting something that's just completely wrong is easier to see if I zoom in. If instead of plotting it over such a wide range of X values, I'm just gonna plot it here. K is not quite, K is here, K is 2 pi. And so it repeats every time I measure it. So here it looks perfectly flat because I sample it exactly once a cycle. So it's always at the same point in the cycle. But here I sample it once per cycle. I sample it not quite once per cycle. I sample it first at the peak of the cycle, then a little bit before the peak, then a little bit more before the peak, then even more before the peak, then more before the peak, until I get to around here where I'm sampling it roughly a quarter of the way through the cycle. Okay, so there's a little bit of a gap. I'm not getting it exactly once a cycle. I'm getting it a little bit more and more and more and more before the peak. And so it's decreasing. Until out here, I've gotten it at the bottom of the cycle. So we see an oscillation with a very long wavelength, even though in fact it has a very short wavelength. And this is like the video of the helicopter blades or the airplane propeller that I showed you last time. You know, you think about the camera as just taking, well, literally snapshots, okay? And if the blade goes around exactly once per frame or exactly twice per frame or exactly 3 times per frame, then it'll look like it's standing still. And if it goes around ever so slightly more or ever so slightly less than once a frame, either way, then it'll be a little bit off in the next frame and off a little more in the next frame and off even a little more in the frame after that. And this phenomenon is called aliasing. It's also called a moire pattern. You've seen this if you've ever looked at, say, 2 screen doors on top of each other, okay? Or if you look at a place where 2 fences are joined, okay? Like if you're walking down the street and you're at a corner and there's a fence along this street and a fence along this street, and you look through the 2 fences, then you can see sort of a weird pattern superposed on the 2 fences because the angle you're looking at them from, the spacing, obviously the fences are built the same, but because you're looking at them from kind of a tilted angle, the spacing looks different. And if the 2 spacings almost match up from the angle you're looking, but not quite, then 2 bars of the fences will be exactly on top of each other. And the next 2 bars will be staggered a little bit. And the next 2 bars will be staggered a little more. And the next 2 bars will be staggered more than that. And you see this all the time. This has applications in physics. A lot of interference phenomena are based on this. Think about the fact that when somebody sends light through a 2-slit pattern, you get these interference fringes on the screen. Now, the actual light has a wavelength that is much smaller than, a few millimeters or centimeters or whatever the spots are separated by on the screen. but at certain points on the screen, they're hitting in sync. And then as you go away, they're just a little bit out of sync. And as you go away further, they're just a little more out of sync, and then a little more out of sync, until eventually you get to a spot where there's an interference minimum. You get zero light because they're now out by exactly half a cycle. Any questions on this? Well, besides being really visually cool, besides just being plain fun to look at, a practical question we can ask is, how often do we need to sample so that we can have a chance of picking up? Now, obviously, ideally, you want to sample many times per cycle. Ideally, if you're watching a process, you'd like to have a really, really fast camera or a really, really fast detector of whatever sort, so that you can see the full up and down pattern. And if you've got a really, really, really fast instrument, then you don't need to ask these questions about what is the fundamental limit to how far I can go. But if you don't have a really, really, really fast instrument, then you're going to be trying to figure out, well, okay, my instrument's kind of slow. What's the best that I can pull out with it? And it turns out that the best you can pull out with it, this might look very confusing, but a computer would be able to resolve this and recognize that there's actually a much faster oscillating pattern. There are mathematical algorithms that you could feed this into, and they would pull out the true oscillation. It turns out that we get, you need to watch it twice per cycle. So right here is where you need to be. Whoa, 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 whoa. Right around here at twice per cycle. So you see peak, trough, peak, trough, peak, trough. That's where you need to be. You need to be sampling at least twice a cycle. That doesn't mean that a computer is going to do a great job at pulling out what's really going on. That doesn't mean that you're going to have a perfectly clean interpretation, but it's your best hope of getting anything at all. And there's a name for this. It's called the Nyquist frequency. If you're sampling at the Nyquist frequency, which means that you're sampling at a rate of twice per cycle, that is the fastest process that you can see. Ideally, you would be sampling more than twice per cycle, which means you'd be watching a slower process. You may be thinking, wait, sampling more means we're slower? No, it means that if I've got my detector fixed, my detector is just going like one, da, 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 it's ticking, it's sampling at this constant rate. If the process I'm watching is such that I get 2 samples in one cycle, I have a chance of detecting it. But if the process I'm watching is happening faster than once every 2 cycles, if it's happening multiple times every 2 cycles of my detector, there's no way I can get anything accurate. If it's happening much slower so that my detector gets many data points, then we have a chance. Any questions? Now keep in mind, sampling at the Nyquist frequency doesn't mean you're guaranteed to get good things. It's just that is the absolute farthest you can go. If I'm sampling twice per cycle, but I've got the phase wrong, I could be sampling twice per cycle when the frequency, I could be sampling twice per cycle, say, let me just put this in, 3.14. There. If I happen to be sampling twice per cycle and I get the 2 zeros in a cycle, I'm totally screwed. The Nyquist frequency, sampling at the Nyquist frequency does not mean that you say, oh, we're fine, we're at the Nyquist frequency. Sampling at the Nyquist frequency means this is as far as we can possibly go. And if we've got the phases set up wrong, we might not even get that. One other thing, I'm going to take this out to say pi over 4 now, because I want it to be easy to get to a limit and know that I'm there. Let's say that I've got a wave like this. Let's say I then switch to minus pi over 4. No, wait, I've got to do it. I've got to do it like that. Never mind. Sorry. When you do these numerical Fourier transforms, right, it turns out that if you're at the highest possible positive frequency, that gives you exactly the same results as being at the largest possible negative frequency. If you're somewhere else, you can get phase shifts that'll make things look different. But it turns out that a frequency, that the highest possible negative frequency and the highest possible positive frequency are the same, basically because adding 2 pi to the frequency doesn't change anything. All right, and here's what I mean. We've got something that looks like this. It's up, down, up, down, up, down, up, down. The underlying oscillation in blue looks totally different. The underlying oscillation in blue is more complicated, excuse me. But I've got something that I sampled once per second, and it's just up, down, up, down. Now, I'm going to add 2 pi to the frequency of the thing that I'm sampling. And it's again up, down, up, down, up, down, up, down, up, down. And so even though I changed the actual signal, even though I added 2 pi to the frequency of the thing that's actually going into my detector, adding 2 pi to it didn't change anything. I still get the exact same measurement. Now you could say, well, of course, you already told us that if we're at a really high frequency, we're not going to see things. Yeah, if we're at a really high frequency, we're not going to see everything. But here's another really high frequency, and we're seeing something strange, okay? So being at a high frequency means being at a frequency that's too high for you to really measure means that you might not be getting accurate data, but at least different high frequencies give different data. I mean, this is clearly a different pattern of red dots than this, even though they're both at really high frequencies. But this pattern of red dots, up, down, up, down, up, down, when I'm at a frequency of 3 pi, is exactly the same as I would get at a frequency of pi, up, down, up, down, up, down. That matters less in experiments because people deliberately don't work at the Nyquist frequency. It matters more in solid state physics when it turns out that certain electron wave functions, if I have an electron wave function at this frequency or a frequency of whatever plus 2 pi over the spacing of the atoms, and you could think of the spacing of the atoms as being really as small as you can resolve, that's equivalent. So this idea will matter. You'll see this if you study waves in periodic systems. Yesterday, I posted a link to a book on Blackboard, a book on something called photonic crystals. This is the beginnings of a concept called the Brillouin zone. I'm not going to explain the Brillouin zone because I'd have to take the rest of today's class and probably next week's classes as well. But this is just the very beginnings of it. Any idea? Any questions? if nothing else, take this away from the past 2 weeks. Fourier transforms are on the one hand just some math, meaning that there are a set of integrals that you can do to change one function into another. But when you do those integrals to change one function into another, yes, you get different ways to represent a function, and that's really, really important, especially on a theoretical level. But playing with those integrals has also enabled us over the past couple of weeks to derive a bunch of experimental insights, to derive insights into why it is that, say, if you've got some incoming data with a certain range of frequency, some incoming signal, excuse me, with a certain range of frequencies, and an instrument with a finite frequency response, the spectrum of your data gets broader, not narrower. And that broader spectrum makes it harder, sorry, it gets narrower. It gets broader in the time domain, narrower in the frequency domain. And that makes it harder to, get good resolution. You should take away the fact that when you try to deconvolve data, when you try to undo that process of convolution that always happens when you send a real signal into a real instrument, that you're going to eventually have a division by zero problem if you try to recover really high frequencies. And that's going to limit just how far you can go and say, well, okay, I know what my instrument does to the signal. So I'll just undo that, and then I'll just get out what the real signal was. The problem is that the real signal has high frequency noise in it. And when you divide that high frequency noise by the high frequency response of your instrument, you get a division by zero problem. Should also take away that we can use Fourier transforms to understand diffraction patterns in optics, and that we can use these ideas of Fourier transforms and sampling to understand what is the maximum rate that we can get data out of a system. What is the maximum frequency of a signal that we can detect? So Fourier transforms are more than just a set of integral tricks that we do to, transform and then inverse transform some functions. They're the foundation for a lot of how we understand experimental data. And that's why I had you buy that second book. And if at the end of the semester you say, I really need to sell a book back, then sell a book back. But if you can keep one book, keep the Fourier transform book, because that stuff shows up all over the place, everywhere from the most pure realms of theoretical physics, where we take functions and represent them as Fourier transforms. And like my favorite quantum optics book has a couple chapters that are mostly on how to do Fourier transforms of vector functions to really disentangle the different parts of the electric field and do the theory correctly. So it shows up there in very pure realms of theoretical physics, and it shows up in the most practical signal processing you can imagine, and everywhere in between. Any other questions? Okay, seeing none, we are going to switch to differential equations. And so what we're going to be doing today and Monday is reviewing some techniques for solving differential equations. I'm not going to try to reteach several weeks of differential equations, but I want to review some key points about initial conditions, linearity, coefficients, and series solutions. And then the week after next, we will solve different equations with series, and we'll find that these series lead us to some polynomials like the Legendre polynomials, which you've seen before. And now we'll see how they're tied into solving the wave equation, or we'll see how some of these series lead to infinite polynomials like the Bessel function, which is also used to solve the wave equation. And then in the last week, we'll put all of that together and understand how we would break a solution to the wave equation into pieces. All right, let's start with a simple first order ordinary differential equation. dv dt plus gamma v equals minus g plus a naught cosine omega t. And I picked this form both because it's a simple linear, it might not look simple, but believe me, compared to some first order differential equations, it is. It's a linear equation, so it has a lot of properties that we want to understand. But it also is something that you will see in mechanics next semester. Here we've got acceleration. Here we've got minus the drag force. Here we've got the gravitational force. And here we've got some, or I guess the drag force over m minus F grav over m. And here we've got some external force that's acting on this particle. And you can say, well, shouldn't I really be writing it as dv dt equals minus gamma v m dv dt equals minus m gamma v minus mg plus m a naught cosine omega t. Sure, if I want to express things in the form of Newton's law, MA, MAX, because this is a one-dimensional problem, and FX, probably Y actually, because gravitational force. But anyway, we've got acceleration, mass times acceleration equals a force. As a physical statement, that's all we need to know. But I'm going to rearrange this. That should have been V there. I'm going to rearrange this so that we've got everything that involves V on one side and everything that doesn't involve V on the other side. This is a differential equation. It's called a differential equation because it's an equation that involves derivatives. What does it mean when I say that this is a first order differential equation? Instead of second order or third order.
The derivative is only it's the first derivative, not the second, third, or fourth.
Yep, and that was also in the chats. Thank you, everyone. It only involves first derivatives. Now, what if I replace this with gamma v squared? Is it still a first order equation or is it something else?
Still first order.
Yep, because it still only has a first derivative. The order of a differential equation depends on the derivatives, not on the other things. I could have v to the 17th for God only knows what reason. It wouldn't change the fact that it's a first order equation. It's also linear, at least if I don't have gamma v squared in there. It's linear because it's linear in v and its derivatives. Of course, it's not a linear function of time. This is a nonlinear function of time. But that doesn't matter, all right? It turns out that most of the interesting properties of a differential equation depend not on whether the differential equation is linear in, say, time, linear in the independent variable. It only depends on whether it's linear in the function that you're trying to figure out. We're trying to solve for V. V is our unknown. This is linear in our unknown. That's what matters. The fact that it's linear in our unknown makes it possible to solve. Now, can somebody tell me the difference between a homogeneous and an inhomogeneous differential equation?
I think one is equal to 0 and one isn't equal to 0, right?
Well, what is equal to 0 in that equation?
The The homogeneous one is equal to 0, and the inhomogeneous one is not equal to 0, I think.
Everything in the homogeneous equation equal to 0, or a certain combination of things?
The combination, because things are adding.
It's the side that has the unknown function, okay? A homogeneous equation can be written crudely as things involving our unknown function, but not time, equals 0. And then an inhomogeneous equation could be written as things involving unknown function equals some function of time. And actually, I'm going to leave this out because that's not always true. We have an inhomogeneous equation here. But the interesting thing about an inhomogeneous equation is that if V obeys an inhomogeneous equation, then V1 plus VP I'll write it this way. Constant times VH plus VP is a valid solution, where VH is the solution to the homogeneous equation. And this is called the particular solution. So any constant times a solution to the homogeneous equation is still a solution to the homogeneous equation, because I could write this as H of V equals 0, where H of V means that I take some, if V obeys a linear homogeneous equation, then I will write that as L of V equals 0, because I can write a general linear first order homogeneous equation as C1 of T dV dt, something involving time multiplied by dV dt plus C0 of T. And I'm calling this 1 because it involves the first derivative, and 0 because it involves no derivative. All right, well then I could replace V with A times V, where V is a constant. And I would get C1 of T A dV dt plus C0 of T times AV equals 0. Because if I just cancel out the constant, I still get the original thing. So if I have a linear homogeneous equation and I take some solution to the homogeneous equation, and I multiply it by a constant, I still have a solution to the linear homogeneous equation. Because I take that combination of derivatives in the original function, I get 0. I multiply a constant by 0. Well, I multiply by a constant, and I still have 0. All right, and more generally, if V1 and V2 both solve a linear homogeneous equation, then A V1 plus B V2 also solve. Let's consider an example. D squared y by dt squared plus omega squared y equals 0. Y equals cosine omega t is a valid solution. It's not the only valid solution, but it is a valid solution. Y equals sine omega t is a valid solution. Y equals a cosine omega t plus b sine omega t is still valid. Can you see why this is a valid solution? Second derivative of cosine is just minus omega, or cosine omega t is just minus omega squared cosine omega t. Ditto for sine omega t. All right. So both of these are solutions to this equation, and adding them together, it's a linear equation. So it's a linear equation with right-hand side 0. So adding 2 more of them gives me another valid solution. Any questions so far? What if I had d squared y by dt squared plus omega squared y equals minus g? And that could be a perfectly valid equation for a mass on a spring in a gravitational field. All right. We got mg pointing down. We've got m omega squared y minus m omega squared y, the restoring force. So that could be a perfectly valid equation. Does cosine omega t solve this equation? If I take the second derivative of cosine omega t, I get minus omega squared cosine omega t. If I add to that omega squared y, or omega squared cosine omega t, I get 0. So no, that's not a solution to this equation. We're going to talk in a few minutes about general ways to solve many homogeneous equations. Inhomogeneous equations are solved by a very valid, rigorous, and systematic technique called guess and check. All right? It turns out that if I were to guess and check that the particular solution to this is a constant, which I'm going to call c. Well, d squared c by dt squared is second derivative of constant is, let's see, nothing, then take the derivative of the nothing. That would be 0. And so I'm left with omega squared c equals minus g, or c equals minus g over omega squared. So d squared c by dt squared plus omega squared c equals minus g if c equals minus g over omega squared. So my particular solution is minus g over omega squared. Now, you could say, all right, well, we found a particular solution and we found some inhomogeneous solutions. Are we done?
Now we have to check it.
Well, we could check it. I mean, all right, I'm just gonna guess something right now. Y equals 3 cosine omega t plus 4 sine omega t minus g over omega squared. D squared y by dt squared will be, let's see, derivative of 3 cosine omega t is minus 3 omega squared cosine omega t. Second derivative of this will be minus 4 omega squared sine omega t. Derivative of this is 0. Looks like they add up to minus g. But are we done? Is that all there is to solving a differential equation? Because somebody else comes along and says, all right, 3 cosine omega t plus 4 sine omega t minus g over omega squared. Yeah, that solves it. But so does 42 cosine of omega t minus 14,605 sine of omega t minus g over omega squared. And I'm not going to write out all of that, mostly because I don't want to write down 14,605 2 times. But we can plug that in and that also solves it. So this other person is coming along and saying, hey, I came up with another valid solution. And then somebody else comes along and says, well, I say pi times I times cosine omega t minus 42 sine of omega t minus g over omega squared. And then somebody else comes along and says lucky 13 cosine of omega t minus 72i sine of omega t. And people keep on throwing these things at you all day long. How do we choose between them? What's another important thing in solving a differential equation?
Euler's identity?
No, not Euler's identity.
Initial conditions.
Initial conditions. An nth order ODE needs an initial conditions, right? Because otherwise people could just come along all day long and keep spitting constants at you. Somebody else could be like, well, I'm going to the alternative universe where we try 14,606 conditions and we find 2 scenarios where Thanos loses instead of 1. So you need to have some way of choosing among these. And I'm going to give you a simple qualitative argument for why we need initial conditions, because it ties into things that some of you may be learning in computational physics. Let's start off with, let's go back to the equation we had. dv dt equals minus gamma v minus g plus a naught cosine omega t. Right? I can write the left side. If we're going to, when we solve a differential equation on a computer, we solve it in time steps. 0 delta t, 2 delta t, 3 delta t, 4 delta t, etc. And somebody could say, what about adaptive step size solvers? Yeah, we're not going to worry about that right now. I'm illustrating a point. So you got y of 0. We're given y of 0, or in this case, it would be v. Yeah. We're given v of 0. And I rewrite this as v of delta t minus v of 0 over delta t equals minus gamma v of 0 minus g plus a naught cosine of 0. And so I get that v of delta t, I multiply both sides by delta t, so I multiply all of that by delta t, is equal to delta t minus gamma v of 0 minus g plus a naught cosine of 0 plus v of 0. All right, but the only way I can do this, the only way that I could go from, that I can figure out what the value of v is at the next time step is if someone gives this to me. Otherwise, I can't figure it out at the next time step. And at this point, someone might say, well, technically, you don't want to use Euler's method. You probably want to use Runge-Kutta. Sure, but all the Runge-Kutta steps follow the same basic logic. And if you don't know what Runge-Kutta is, don't worry. That's for people taking computational physics. Okay, now I want to find it at the next time step. So I say v of 2 delta t minus v of delta t over delta t equals minus gamma times v of delta t minus g plus a naught cosine of delta t. And then I would just do all of the same steps again. And if you're thinking this is really tedious to write out, you're absolutely correct, which is why we program computers to do this. But we wouldn't be able to get those codes to run if we didn't have some initial value to start it with. Because however confusing you humans find algebraic symbols, computers find algebraic symbols even more confusing. Even Mathematica would, if asked to give an actual number that you could use to actually do something, would say, I like don't know. And Mathematica would be right to say that because it wasn't given the input. All right, so to solve a first order differential equation, this is how you do it. At the end of the day, on a computer, you need an initial condition, and then you can find v of delta t, and then you can find v of 2 delta t, and so forth. So every differential equation needs an initial condition. If we had a second order equation, we'd be writing out second derivatives. We would need v of 0 and dv dt at t equals 0. If we had a third order equation, we would need 3 initial conditions, and so forth. Any questions? Now, there are many, many types of differential equations. And the textbook goes through all of the conceivable first order differential equations that you could encounter. But a lot of the most important differential equations in physics are second order. Newton's laws, because acceleration is a second derivative of position. The wave equation, second derivatives with respect to both time and coordinates. The diffusion equation, second derivatives with respect to coordinates, first derivative with respect to time. Laplace's equation, second derivative with respect to all of the coordinates. Let me get rid of that message. So let's focus on second order equations here. And let's start with linear second order equation with constant coefficients. Because it turns out that such equations show up all the time. If we have md squared x by dt squared equals minus kx, this is mass times acceleration. This is a spring force. Minus beta times the velocity. This is a drag force. And we will eventually add F naught cosine omega t, an external drive force. This shows up all the time. And even in the real world, where you don't spend a lot of time thinking about masses on springs, equations like this show up in circuits. Equations like this can be simple models for electromagnetic waves in a cavity. Once you may be thinking, well, how is that possible? An electromagnetic wave in a cavity is a function of 4 variables, x, y, z, and t. But if we represent that with, say, just some approximation, we can reduce this to dealing with a few coefficients, like we talked about with Fourier series. More on that in a few weeks. So I could rewrite this as minus kx minus beta dx dt plus f of t driving force, or rewrite as md squared x dt squared plus beta dx dt plus kx equals f of t. And we will initially, 0 for now, i.e. homogeneous equation. And because this is linear, a linear second order equation, it has 2 linearly independent solutions. Does anybody remember how to find the solutions to a linear equation with constant coefficients?
Don't you define like a characteristic equation from the?
Yeah, we need a characteristic equation. So let's guess. We guess that x of t is e to the lambda t. And then we plug it in. All right, so dx dt will, well, the derivative of an exponential is just the exponential. And then we have to use the chain rule to get the derivative of the exponent. So lambda e to the lambda t. And d squared x by dt squared is just going to be lambda squared e to the lambda t. And so we're going to get m lambda squared plus beta lambda plus k whole thing times e to the lambda t equals 0. You can cancel that. It tweeted something terrible, and we're all in a bad mood today, so we cancel it. And now we just have an equation to solve for lambda. This is a quadratic equation. So lambda is minus the coefficient of the linear term, minus beta, plus or minus, that came out wrong, plus or minus the square root of beta squared minus 4mk. Let me questions on how I did that? Hopefully this looks somewhat familiar from your differential equations class, but you may be thinking, if I've got a mass on a spring, don't I get an oscillation? This doesn't look like an oscillation. This looks like just an exponential function. Well, yeah, but exponential functions can be oscillating. What does it take for an exponential function to oscillate?
Imaginary?
Yeah, it needs to
Yeah, we
be.
need an imaginary or complex exponent. Beta is probably not imaginary. But if it turns out that beta is small and 4mk is large, then this could work. So what people usually do is they write it like this. I can always multiply by -1 twice. Right? There's no rule against multiplying by -1 twice. And so if I multiply by -1 twice, one of those -1s, I'm going to take the square root of, and I'm going to get minus beta plus or minus I square root. But then I'm going to leave the other -1 in there. I'm going to get 4mk minus beta squared all over 2m. And then we usually do one other thing. We write beta over 2m plus or minus I. 2m outside of a square root is the same as 4m squared under a square root. So I'm going to write this as 4mk over 4m squared and minus beta squared over 4m squared. And what do you know? The 4 did something terrible on Twitter, so it gets canceled. And I am left with minus beta over 2m plus or minus I square root of k over m minus beta over 2m squared. And this should look familiar if we took the case that beta equals 0, because beta is basically a frictional drag force. If beta equals 0, we just get plus or minus I square root of k over m. And if you think way back to freshman physics, what's the square root of k over m? What's the square root of spring constant over mass?
Omega squared, or yeah, just omega.
It's omega. It's omega. And this is how we handle any of these equations. So we could say that x of t is equal to c1 e to the minus beta over 2m t e to the plus I square root of yada, 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 plus c2 e to the minus beta t over 2m e to the minus I square root of yada, yada, yada. And yes, I yada, yada the best part, to quote Seinfeld. So that's how we solve these kinds of equations. Now we still have to deal with initial conditions, and I'll let you deal with initial conditions in Friday's activity and try to understand how we use initial conditions to pick these coefficients. But basically we would be given x of 0 and dx dt at t equals 0. And so we'd have to just plug in 0 and evaluate x, and then evaluate the derivative and plug in 0. And the value of x at t equals 0 will depend on c1 and c2. And the derivative at t equals 0 will depend on C1 and C2 and maybe some other messy things. And then we would use that to figure out what C1 and C2 must be equal to. Any questions? Now, one very important thing is that I've been saying that solutions to linear homogeneous equations should be differential equations. Solutions to linear homogeneous differential equations can be written as sums of n linearly independent functions. If I have a second order equation, there must be two linearly independent functions that will solve that equation. And here there clearly are, because we've got two different values of lambda. We've got e to the lambda 1t, e to the lambda 2t. And as long as those lambdas are different, we have two linearly independent solutions. And likewise, if it weren't beta and omega, sorry, if it weren't beta and k and m, if we called our coefficients something else, still, we'd have e to the lambda 1t, e to the lambda 2t. Those would be our two independent solutions. And this idea, this should be reminding you of linear algebra right now. Okay, when I keep saying that we have a sum of n linearly independent solutions, that is why they put linear, that's why they put linear algebra and differential equations in the same class in the math department. That's why they teach them together. And this idea is something that we go basically all the way with in quantum mechanics. In quantum mechanics, they talk nonstop about vector spaces of solutions. It's the most important idea that you'll use over and over and over again. So the linear independence of these solutions is tremendously important. It's also pretty important in classical mechanics when you get to normal modes of oscillations where you've got systems of several masses and springs. And you may be thinking, how often in the real world do I care about several masses and springs? Well, if it's masses and springs like you see in a freshman lab, probably not. If it's a way of saying that if it's a simple model for a device that's going to go on a rocket and there are coupled modes of vibration and you have to damp out those vibrations so that vibrational energy doesn't build up and destroy the apparatus that you put on there, yeah, it's important. If it's a model of energy exchange between two modes of an optical resonator, it's pretty important. If it's a model of a molecule as a bunch of masses and springs, people can go a long way with models of molecules as masses and springs. But there is a problem here. I keep saying as long as we have two different values of lambda, can anybody look at this and see a situation where my value of lambda might not have two distinct values of lambda?
Do you mean like if lambda is equal to 1?
Well, lambda doesn't have to be equal to 1. Lambda could be all sorts of things, but still not have two distinct values of lambda.
If your equation is just first order.
If it's a degenerate,
If it's degenerate, yeah, we could easily have a second order equation that only has one root. I mean, look at what we've got here, okay? If the thing underneath the square root was 0, then we'd have minus beta plus or minus I times 0, which would be, hang on, nothing times the square root is nothing, nothing times the I, nothing. So we have to be careful. What if our solutions are degenerate. Then e to the lambda t and t e to the lambda t are both solutions. Okay, it's a very special, rare case, but it happens. And it's something that you might have to worry about if a system is right on the edge. It's something that shows up in the design of optical tables. Ideally, you want an optical table to be overdamped, meaning that if you shake it, its behavior will be a purely exponential decay towards equilibrium. You don't want it to be an oscillating decay towards equilibrium, because an oscillating decay towards equilibrium means everything on the tabletop is oscillating. Ideally, it's just a gentle decay towards equilibrium, but it could be critically damped. And if it's critically damped, that means you should probably overdamp it more, but then you'll see a little bit more complicated behavior, and these two functions show up. And I'm going to put that on probably Friday's recitation and also some homework for you to do. Any questions before we go to one more type of equation that is basically a very simple version of what we're going to deal with next week? Any questions at all? Well, let me give you an equation that this in and of itself doesn't show up a lot in physics. This is just a purely mathematical toy, but it's a mathematical toy version of something that does show up. If we make it more complicated, which we will do next week and the week after, then it shows up all the time in physics. This equation, it's called the Euler equation. And it turns out that we can just guess a solution. We will guess that y equals t to the n. Now here's why we would guess that. If I take a derivative of a power, what do I get? If I take a derivative of t to the n, I get I get n times t to the n minus 1. If I multiply by t, I get back nt to the n. And if I take the second derivative, then I get n times n minus 1, t to the n minus 2. And if I multiply by t squared, I get n times n minus 1, t to the n. And so if I add at squared d squared y dt squared plus bt dy dt plus cy, every term just has some constant times t to the n. All right? So I'm adding up t to the n again and again, multiplied by different constants. And as long as those constants all cancel each other out, then we satisfy our equation. And you can say, all right, but you're just guessing that. Yeah, I'm just guessing that, but it's a guess that works. And there is a theorem that linear homogeneous differential equations of second order have exactly two linearly independent solutions. So if I find these two power laws and they worked, who cares if I just guessed, okay? If that guess is right, then there's a theorem which tells us that our guess covers everything we need to know. So that's going to be a n times n minus 1 plus bn plus c equals 0. Okay, we've got an equation for n here. Okay, we've got a quadratic equation. We've got an squared minus an plus bn plus c equals 0. Or an squared plus b minus a n plus c equals 0. So n is equal to negative the coefficient of the linear term All right, and we've only got a minute left, so I'm not going to go through too many examples, but I'll ask you to check some of that on Monday's practice assignment. Because if you can do this, if you are comfortable manipulating these kinds of formulas, then you will be comfortable manipulating the formulas that we're going to get on Monday when we deal with power series. And if you're comfortable solving equations with power series, then you'll be comfortable solving the types of partial differential equations that what just happened? I did not want that to come on. You'll be comfortable dealing with the kinds of power series that we get when we solve the wave equation in different coordinate systems. And that will take us to Legendre polynomials and Bessel functions. Last thing, very last thing. This could also wind up having degenerate solutions. What if this whole thing were 0? Then y is just x to the a minus b over 2a. And you're thinking, isn't it b minus a, but there's a minus sign there. We've only got one power. It turns out that there is one other solution. And you will see this sometimes in the theory of certain kinds of Bessel functions, certain kinds of solutions to similar but more complicated equations, where your two linearly independent solutions are either a function that we know about or a logarithm multiplied by that function. Any questions? All right, I'll see you Friday. We'll work on an activity practicing with solutions to differential equations. Have a good day.
Thank you, Professor.
You're welcome.
Yep. Thanks, Dr. Small.
You're welcome. Andrew, Demetrius, did either of you have a question? All right, then I'm going to log off. Have a good day.